What we are going to talk about first today is the concept of instantaneous power and average power in, power in multi-frequency circuits. And this is going to be a lot of math and bookkeeping, really. So I'm going to draw your attention to two trig identities that we are going to utilize. The first of which we used, I believe, last Friday, and it was A cosine angle 1 times B cosine angle 2 is equal to 1/2 AB times cosine angle 1 minus angle 2 plus cosine angle 1 plus angle 2. And the second identity that we're going to need to pay attention to is that cosine of negative x is the same as cosine of x. So let's say that we have a generic black box network like so. Over which we apply some source voltage Vs, and we measure voltage V of t across the terminals of the network and a current I of t flowing into the network. And I am absolutely aware that this is exactly what we did last Friday, I believe. But in this case, we're going to say that V of t is of the form Vm1 cosine omega 1 t plus theta V1 plus Vm2 cosine omega 2t, excuse me, I need to open that parentheses back up, plus theta V2 at two distinct frequencies, representative of a multi-frequency circuit having two excitation frequencies. We are going to limit our discussion to only two frequencies because, as you will very quickly see, the math is going to get horrifying. Our current I of t will then be of the form Im1 cosine omega 1t plus theta I1 plus Im2 cosine omega 2t plus theta I2. And what I'm going to do is I'm going to break these parts down into constituent bits. So I'm going to call this guy right here VA of t, actually V1 of t. Guy right here V2 of t. This guy down here, I1 of t. And this guy here, I2 of t. Using these designations, our instantaneous power, P of t, is simply the product of V of t times I of t, or V1 times I1 plus V1 times I2 plus V2 times I1 plus V2 times I2. And as you can imagine, all of this cross multiplication effectively of sinusoids is going to make our resultant here, our expression for our instantaneous power, quite a monstrous equation. Okay. So let's start with V1 times I1. Okay. So in this case, V1 and I1 both have the same frequency. As we observed last Friday, I believe, that means that the product of V1 and I1 is going to give us a DC term and a twice omega 1 term, okay? So that's going to look like 1/2 VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM1 IM1 cosine twice omega 1t plus theta V1 plus theta I1. For our next multiplication, we are going to have dissimilar frequencies or non-equal frequencies. So we're going to wind up with two terms, one of which is the difference of omega 1 and omega 2, and the other of which winds up representing the sum of omega 1 and omega 2. So adding to our previous bit, we're going to have 1/2 VM1 IM2 cosine, and so now you need to pay attention, right? Angle 1 in this case is omega t plus theta V1. We're lumping that all together and considering it an angle. Angle 2 is omega 2t plus theta I2. So if we take angle 1 minus angle 2, what that's going to look like is omega 1 minus omega 2 quantity multiplied by t plus theta V1 minus theta I2. I do this all by memory. It's just so much writing. And then we have our frequency term where we add things together. So that's going to be 1/2 VM1 IM2 cosine, sorry, that should not be twice, omega 1 plus omega 2 t plus theta V1 plus theta I2 And I think I have one too many parentheses there, so I'm going to delete that one. I think I've closed things off correctly. So we are halfway through our analysis here, but I wanted to point something out. We have started off with signals that are oscillating at two distinct frequencies, omega-1 and omega-2. And to this point, our power equation is now oscillating at four distinct frequencies. And we're not done. Okay. So I'm now going to do the bit where I multiply V2 times I1. So I'm going to have VM2 IM1 cosine omega-2 minus omega-1t plus theta V2 minus theta I1 plus 1/2 VM2 IM1 cosine omega-2 plus omega-1t plus theta V2 plus theta I1. And so before we move on to the next bit, I want to point something out here. Omega-2 plus omega-1 times t is the same as omega-1 plus omega-2 times t. So these two terms right here, the right-hand side of lines 2 and 3, are actually oscillating at the same frequency. So those two terms can be lumped together using complex math into a single sinusoid oscillating at that particular frequency. Okay? So that bit's fairly straightforward. For this part right here, it may not look like it, but these are also oscillating at the same frequency. So the left-hand term of line 2 and the left-hand term of line 3 are oscillating at the same frequency because the cosine of a negative angle is the same thing as the cosine of a positive angle. So omega-1 minus omega-2 is the exact same thing as negative omega-2 minus omega-1, where we're assuming that omega-2 minus omega-1 in this case is a positive quantity. Okay. So our left-hand term of lines 2 and 3 can be lumped together and considered a single frequency term. Our right-hand terms of lines 2 and 3 can be lumped together and considered a single frequency term. So we're still at 4 frequencies.
So does that mean that theta portions should just add with those common frequencies?
So you wouldn't really add them in the time domain per se. And the reason why I say that is because the math would be very, very difficult. Because if you had, let's just say that you had sine 2t plus 5 degrees, or cosine 2t plus 5 degrees, and cosine 2t plus 10 degrees. How do you add those two together?
Well, it's kind of
Complex numbers.
Yeah.
Yeah.
Complex, okay. Thanks.
So you can't just lump it together as a single term easily here. You would have to use a complex number representation in order to do it. But they do represent oscillations at the same frequency, so that math is possible. But in a time domain representation, this is going to be the easiest way to represent it. All right, lastly, we have our V2 term times I2 term. Okay. And so I believe that's going to yield another DC term. So 1/2 VM2 IM2 cosine theta V2 minus theta I2 plus 1/2 Vm2 Im2 cosine twice omega 2t plus theta v2 plus theta I2. And so we wind up with 5 different frequencies, right? We have DC twice omega 1, twice omega 2, the difference between omega 1 and omega 2, and the sum of omega 1 and omega 2 as our oscillation frequencies. Okay? So I believe how this works out is if we have n frequencies, we're going to wind up with n squared plus, or if n frequencies in our voltage and current terms, we're going to wind up with n squared plus 1 different frequencies that our instantaneous power will oscillate at. Which, this is a lot of work. For anything beyond 2 frequencies, it just gets ridiculous, right? It's why we don't really pay a whole heck of a lot of attention to instantaneous power. And instead, we start using quantities like RMS representations of our signals in order to calculate average power and things like that, because the derivation here was wildly annoying. Now, one thing that I do want to point out and this is a very interesting result. These 2 terms that I have right here that I've underlined in blue, added together, represent the average power absorbed by our network. Okay. What is very interesting about this result is because this is the exact result that we would get if we used the superposition technique to erroneously calculate power. What I mean by that is that power is inherently a nonlinear quantity because it depends on the product of voltage and current, or you can think of it as proportional to the voltage squared, or proportional to the current squared, which is inherently a nonlinear trait. But because all of these cross-frequency terms effectively die out when you take their average values, right? So if I wanted to take the average value of this bit right here, the top right expression in line number 1 of the solution, for those of you who are on Zoom and can't see me tapping the board. If I wanted to take the average power of this term right here, well, it has to be 0, because if I integrate the sinusoidal function over exactly 1 period, the area under the curve is 0. Every term in this in which a t survives has an average value of 0. Okay, we're going to use that in a little bit when we get into our discussion of effective values. But I'm just pointing it out here because we shouldn't be able to use the superposition principle to calculate power. But in this particular case, where we have purely sinusoidal excitations occurring and multiple purely sinusoidal excitations occurring, we can fudge it to get the average power, because all those cross-frequency terms, or all those non-DC terms, actually will wind up canceling each other out. All right, so with this behemoth out of the way, let's talk about effective values, which came about to simplify this horrifying amount of mess. For those of you who had me for 21, the next couple of minutes are going to be review. I mean, it should be a review for everybody, but literally the next thing I'm going to talk about is exactly how I taught it in circuits 1. So you might be bored for 5 minutes, or more bored than usual for 5 minutes, I guess would be a better way to phrase it. So I'm going to try to draw a very terrible picture here. Well, I'm not going to try to draw it terribly, but it's going to wind up being a terrible picture. So what this is meant to be is a standard electrical receptacle, excuse me, like we use here in the States. For those of you that are in the classroom, you can see pairs of these receptacles literally all around the room. There's a couple up here next to me. There's one over there to Catherine's left. There's one over here to Connor's right, one directly across from Drew. You guys are near a column, so I don't think you have one super close by, but you hopefully get the gist of what I'm referring to. So if I were to ask you all what the voltage supplied by one of these receptacles or outlets is, what would you tell me?
DC or AC?
So it's a very interesting question. Is electrical power distributed here in the United States using DC transmission or AC transmission? Pardon? It's AC. Right. It's AC transmission. So how much voltage is supplied by one of these outlets? 120. 120 volts, right? Okay. So chat 120, yes. What I'm going to do here is I'm going to assign some voltages and names to some of these terminals and all this kind of good stuff. All right, so this is going to be the positive polarity terminal on the left, negative polarity terminal on the right. And the consensus from 2 of you guys is that this is 120 volts. I both agree and disagree with that sentiment, okay? So let me explain a couple of things here. Our wire on the left is typically referred to as the neutral wire for a single phase circuit. And it's associated with the larger of the rectangular holes, I guess, in the outlet. And then on the right, we have what's called the hot wire. Okay. And it's associated with a positive polarity terminal of our outlet. And in the bottom, we have our ground wire. And this is typically tied to ground through a bus connection on your load center, or more commonly referred to as your breaker box. And it is then usually tied to a grounding rod that is literally embedded into the earth so that it is physically touching the ground. Okay. So the potential of 120 that you hear when referencing a standard US outlet is the potential difference between the hot wire and the neutral wire. Now, we talked literally just a couple of moments ago about how here in the United States and in the overwhelming majority of the industrialized world, electricity is distributed using AC signals, okay? But we are describing that AC signal with what appears to be a DC voltage. Now, the actual voltage that is being provided by this outlet, I'm going to call it VS of T. It is a time varying quantity because, again, power is distributed as an AC signal. And it has a value. We got some probes and hooked up an oscilloscope of 120 times the square root of 2 cosine 120 pi t plus some phase angle theta v volts, where that phase angle would literally depend on just what point in time or what point in the waveform we happen to start measuring. Okay. That 120 representation is what's known as an RMS voltage. All right. Root means square voltage. And what it represents is a DC signal that delivers the exact same amount of average power to an arbitrary resistor as this time varying signal does. Okay, so they are not equivalent, but they deliver an equivalent amount of power to an arbitrary resistance. Okay. Now these letters RMS tell us the mathematical operation to convert any periodic signal. So it could be a sinusoid, could be square wave, a series of rectangular pulses, literally any signal that is periodic can be represented with an RMS or effective value that will make power calculations easier to carry out than dealing with the waveform itself. Okay. So let's go through these steps to develop our equation. The average power delivered by a DC voltage to a resistor would be the voltage drop across the resistor, and I'm going to call this V effective squared divided by the resistor value itself. Okay. So this is our equation for DC power delivered to a resistor by a voltage. Now let's consider the average power delivered to a resistor if we have a periodic signal. Okay. So for a periodic signal, the average value of that signal is the integral over exactly one period, capital T, of our instantaneous power signal divided by the duration of a period. So that's how we get the average value of any periodic function. Okay? So in this case, our instantaneous power relationship, I'm going to call it Vs. And so our power delivered to a resistor would then be Vs squared divided by R, where again, the quantity Vs is just representative of any periodic voltage signal that is applied across a resistor. So our goal here is to equate these two average powers and solve for the DC quantity V effective in terms of our periodic quantity Vs. And this is actually fairly trivial, right? So if I make these two things equal, I would have V effective squared over R is equal to 1 over T times the integral from 0 to T of Vs squared over R dt. One thing that we can notice right off the bat is that there's a factor of 1 over R on both sides, which means the size of the resistor we're taking the power over doesn't actually matter. So we can cancel those two 1 over R terms out. And then we simply need to take the square root of both sides, and that will give us an expression for V effective in terms of only our periodic voltage waveform. And we find that our effective value is then the square root of 1 over T times the integral from 0 to T of, sorry, it doesn't need to be that high. There we go. Vs of T dt. Now, a couple of minutes ago, I told us how the letters RMS tell us exactly the math that we're going to do to determine this effective value. So let me explain that. RMS, if I didn't mention it earlier, stands for root mean squared. So specifically, we are taking the square root of the arithmetic mean, also known as the average, of the square of our periodic signal. So that's why it's called a root mean square or RMS value. Literally tells us the math to do. Okay. If we were to develop, if we were to develop a relationship for currents, we could follow this exact derivation, except that we would have I effective squared times R, and then IS squared times R here, and we'd wind up getting effectively the exact same equation. So without any particular derivation, we can define an RMS or effective current to be 1 over T times the integral from 0 to T IS squared dt. Now, one thing that I want to point out here is that the limits of my integration, particularly integrating from 0 to T, I don't particularly mean that specifically. What I mean is that we are going to integrate over exactly one period of our waveform. So as long as the bounds of our integration are over one period, we will get the right result. So that's what I'm trying to illustrate by this. I could also call it negative T over 2 to positive t over 2 or lowercase t to lowercase t plus capital T, all of them representing the same thing. We just integrate over exactly one period. So let's take a moment here to mathematically show how we get from this Vs of t to this 120 volts RMS. So if Vs of t is of the form Vm cosine omega t plus theta v, I'm going to show this generically for a sinusoidal waveform having a particular magnitude, a particular oscillation frequency, or a general oscillation frequency, omega, and a general phase angle, theta v. The effective value call is given by the expression the square root of 1 over t times the integral from 0 to t of Vs squared of t dt. So in order to carry out this integration, we need to have an idea, not necessarily of a numerical value of the period of our sinusoid, but an expression that relates the period to the oscillation. So let's talk about that briefly here. Some of you may remember it. I believe we derived it in circuits 1. Others of you may not. So if I were to plot the cosine function, it would look something like this. Arbitrarily, I'm going to say that the distance between the positive peaks here represents the period of the sinusoid, right? Because it's when this signal starts repeating itself. We could just as easily identify the period as the negative peaks, the distance between the negative peaks, the distance between correctly defined zero crossings. So when the waveform crosses 0 and is decreasing, so from here to here would be a period, or when the waveform crosses 0 and is increasing, so from here to here would be a period. And we use lots of different ways to measure the period of a sinusoid when we're doing power, like actual power calculations or physical power calculations, just to give us some idea of our phase angle and all that kind of good stuff. So I'm just mentioning this because I'd be willing to bet at least one of you will wind up using some sort of representation like this in your senior design project a couple of years in the future. Anyway, this period t, the amount of time it takes for exactly one cycle of our waveform to occur, is related to the linear frequency of the circuit as capital T is equal to 1 over f, where f is the linear frequency. So linear frequency says effectively the number of cycles that occur per second, and t is the number of seconds that it takes for one cycle to occur. That's what this relationship is. Well, linear frequency and angular frequency are related as well, right? Angular frequency omega is simply 2 pi f. So omega is the angle per unit time is equal to 2 pi, the amount of angle in one cycle or one circle multiplied by the linear frequency. So we can manipulate this and find that f is equal to omega over 2 pi, and from this, capital T is then equal to 2 pi over omega. And so this is going to give us the bounds of our integration. All right, so 1 over t is going to look like omega over 2 pi. We're going to integrate from 0 to 2 pi over omega. And the signal that we're integrating is Vs squared, which is going to look like 1/2 Vm squared plus 1/2 Vm squared cosine twice omega t plus twice theta v. That's literally just using that trig identity number 1 that we talked about at the top of class. Okay. I can split this integral up into 2 parts. So we would have omega over 2 pi times the integral from 0 to 2 pi over omega of 1/2 Vm squared dt plus the integral from 0 to 2 pi over omega 1/2 Vm squared cosine twice omega t plus twice theta v dt. Close this out. And I'm taking the square root of this whole thing. So let's talk about the right-hand integral here and what it represents. So our picture here represents, that I've drawn up to the top right of the screen right now, represents one period of a sinusoid that is oscillating at a frequency of omega, right? So what I'm going to add to this picture, at least what I'm going to attempt to add, is another sinusoid that's oscillating at twice omega. And arbitrarily, I'm going to give it a phase angle of 0. So twice omega would look something like this. It's literally just 2 times as many cycles in the same amount of time. This second term here is asking me to integrate this green curve over exactly 2 periods of the waveform. So if I integrate a sinusoidal function over any integer number of periods, what is the result of that integration? 0, right? Because exactly half of the time it will be above the horizontal axis and exactly half of the time it will be below the horizontal axis. So this integration right here is simply 0. Throw that part away. And then what I have over here on the left-hand side is literally just constants, right? So I would have the square root of omega over 2 pi multiplied by a factor of 1/2 Vm squared times the integral from 0 to 2 pi over omega of dt. Well, the integral, let me write this out. dt is just t. So this would look like 2 pi over omega minus 0. And we can see that this term and this term cancel each other out, leaving us with the magnitude of our voltage waveform divided by the square root of 2 as our effective value. So that's exactly where that 120 square root of 2 blah blah blah, how and why we get to treat it as 120 volts DC. So the 120 volts DC is the effective value, or 120 volts RMS is the effective value of that sinusoidal waveform. Radel. No, so the VM, yeah, no, so the VM here is simply whatever magnitude the time, the periodic waveform has, right? Or in this case, the sinusoidal waveform. So if we scroll way back up here to the top, 120 square root of 2 divided by square root of 2 is 120.
Oh, okay.
All right. Okay. So I believe I've already put up a homework set wherein I ask you guys to calculate the effective value of a few different commonly used periodic signals in electrical engineering. So I believe I've given you a single problem wherein I ask you to calculate the effective value of a sinusoid, which, and we just did it right here. So you can pretty much copy that exactly. I think I time shift it by a little bit, but you can figure that part out. I also give you a square wave, and I also give you a triangular wave. This is the process by which you'll do it, okay? Sorry, go ahead, Bradley.
Oh, sorry. So whenever we're like demonstrating the calculation, do we need to involve the proof, or can we just use the relationship again?
Do the proof, because I'm giving you specifically a signal where it doesn't have a phase angle of 0, so that you'll need to take that into account. The math will work out to this result, but I want you to show me that it works out to that result. Okay. Another thing that I asked you to do is to determine the effective value of a periodic signal, which you can only determine the effective value of periodic signal, but a periodic signal that is the sum of sinusoidal signals. So like a multi-frequency voltage like we had at the beginning of class. And so we're actually going to use the results of our discussion previously to come up with a generic expression. All right. So I want you to keep effectively what we have right here, what we just did in mind. All right. And I'm going to go back to our horrifying equation. So our effective value was, in a sense, related to our instantaneous power quantity. Because if we just arbitrarily divided this by R, well, actually, no, if we treated all of our I's here as V over R's, we would effectively have the exact same expression. So this is going to look similar to what the voltage waveform squared would look like, okay? If we treated all of our IM1s as an additional VM1 and all of our IM2s as VM2, et cetera, okay? Well, when we take the integral of this thing, as we mentioned previously, the area under the curve for all of the terms that contain a t goes to 0. And all we are left with are these DC terms, effectively. Okay, hold on just a minute, Madeline. So I'm going to generalize an expression for multiple sinusoidal frequencies, okay? I can get my paper thing where I want it to be. So let's say that we have a waveform, V of t is, I'm going to call it Vm naught cosine omega naught t plus theta v naught plus Vm1 cosine omega 1 t plus theta v1 all the way out to Vmn cosine omega nt plus theta vn. So this could be the sum of an infinite number of sinusoids. As long as the omegas work out in such a way that this is a periodic function, what I'm about to show you applies. Okay. The effective value of that waveform is simply going to be actually, let me V effective at omega naught squared plus V effective for omega 1 squared all the way out to V effective for omega n squared. So it's the square root of the sum of the squares of the effective values. So just to be very, very clear about what I mean with my notation, if we had V of t was equal to 8 volts plus 4 cosine 2t plus 10 degrees plus 5 cosine 4t plus 30 degrees, the effective value would be given by, and let's talk our way through this. What's the effective value of 8 volts? Just 8 volts. Okay, the effective value of a DC term is a DC term because the whole point of an effective value is to give you the DC equivalent that delivers the same amount of power. So the DC equivalent of 8 volts is 8 volts. All right. What's the effective value of 4 cosine 2t plus 10 degrees? 4 over the square root of 2. What's the effective value of 5 cosine 4t plus 30 degrees? 5 over square root of 2. So the effective value would then be calculated just by performing this mathematical operation. It may not be obvious, but a DC term does satisfy our constraints of adding together the sum of sinusoids, because a DC term can be thought of as oscillating at an angular frequency of 0 radians per second. All right, so what we have talked about today was the instantaneous and average power absorbed in a multi-frequency circuit. And I constrained that discussion to only 2 frequencies, just because I'm not that much of a masochist, I guess. There's really no need to go beyond that point. Then we have introduced the concept of effective values for periodic waveforms. Just to reiterate, the equations that we developed here, this guy for V effective and I effective in the bottom right-hand corner of the screen, are valid for any and every periodic voltage and current waveform. For a purely sinusoidal signal, we found that the effective value is simply the magnitude of the signal divided by the square root of 2. Now, this is actually pretty interesting, and I kind of skipped over it, so I'd like to talk about it for a moment as we're wrapping things up here. We derived this expression using a generic waveform where we don't know what omega is and we don't know what the phase angle is. And we found out that the result is completely independent of the angular frequency and the phase angle. That's actually a very, very good thing, okay? So the reason why I say that is if you were trying to design some sort of power system like I've had to do in the past for regions outside of the United States, where power isn't distributed using a 60 hertz AC standard, using effective values means that your frequency doesn't particularly matter. All of your relationships will still get to work, and so you can just work in this RMS domain without having to deal with all the other consequences, right? This is particularly great in places like Japan. So here in the US, we use 60 hertz distribution. In the overwhelming majority of Europe, they use a 50 hertz distribution. Well, in Japan, as it was occupied by both the United States and European forces after World War II, what happened when their power infrastructure got built back up after the bombings was that everywhere north of the river used one frequency And everywhere south of the river wound up using the second frequency because they're occupied by different coalition forces. So there are frequency conversion stations across the river that connect the grid. So using RMS values to design electronics for Japan is much, much better than having to deal with time domain signals where you would have to take into account how does it behave at this frequency versus how does it behave at that. So anyway, that's just a historical anecdote that kind of helps explain why electrical engineers have chosen to effectively rewrite the rules for power using effective values. And that's going to be our topic for Wednesday's class, when we get into using these effective values to come up with the concept of complex power and then analyze its constituent parts. So that's enough out of me for today. Brad.
So when we're doing the homework, at what point do you want us to start?
From the beginning. Like, so by that, I mean, you are using this equation. So this is the beginning. You don't need to derive the equation, but this is the equation that is used to determine the effective value. And you should use this for every one of the problems except for when you specifically have a voltage waveform that is the sum of sinusoids. I don't want you to derive this. You can just apply this equation directly. Is that clear? All right.
Is that the same equation that's used for like adding vectors?
It's pretty similar. You could think of it. Let me see what's going on in the chat here real quick. When will today's class video be posted? I hope to have it up tomorrow. I make no guarantee of that whatsoever, but I hope to have it up tomorrow.